This is an introductory video to Nevara CycloR tools version 3.0. So I'll explain how to use this software basically. So I believe you have some kind of understanding on what is Cyclo-rotor. So in left hand side you have the input panel. So here you can input all the details regarding the cyclo-rotor. Here we have considered the link parameters like what is the length of these rods. So please note that the dimensions are from meters. So and apart from the length of these foldings, you can actually select three aerofoils here. So currently we have only two working airfoils, which is Naga 15 and Naga 12. 16 Naga 16 is not available in this particular version. We hope to include that also in future versions. So again, you can also consider how many blades you need to include in this uh, cyclo setup, and also you can select the span length and also the RPM. So there's another parameter which is the density of the air, which we consider it as 1.2 as a constant. It's hard coded. We will also include it as an input in future. So what we have to do is we can basically input these parameters. Once you have some idea like what kind of parameter you should include, uh, you can you press this calculate button in order to see the performance. So by default you have one specific set of data regarding a specific cyclo-rotor. This is just normal cyclo-rotor, not anything specific or some better performance. So you can actually customize your data. So once you customize your data, you can click calculate, and what it will do is it will take 2 to 3 seconds, and it will create your cyclo-rotor plot. So as you can see here, we have the plot 2, and the plot 2 is actually regarding the data you entered. So uh, so if I go to a specific plot or a specific cyclo configuration, so first thing you can see is the details about your airfoil. So like since the airfoil is the most important factor of the cyclo-rotor, so here we included the lift coefficient and the drag coefficient variation with the attack angle. So it is the first plot of every configuration. So it won't change if you don't change the aerofoil, but if you change it, you'll see variations of this curve. So in the top we have the lift coefficient, and in the bottom we have the drag coefficient. Please make sure that this program assumes that you are in order to get correct results, you have used some kind of configuration which the maximum attack angle falls between -20 to positive 20. Like your angle of attack should not go beyond that range. And if it go beyond that range, what will happen is, as you can see here, it will incorporate the rest of this curve. You can actually do manipulation to these graph windows. It will interpolate the rest of the curve, and it won't the values you get be incorrect. And this does not consider any kind of turbulence effect which happens in these regions, and this is only representing the data regarding this range for both left and right. So in the second graph, we have the pitch angle was azimuth angle graph. So basically, the azimuth angle is the angle which your cyclotor turn, and the pitch angle is the angle is the true angle of attack of the cyclotor blade. So like when it rotates along the cyclotor, your angle of attack changes, and so according to the azimuth angle, we can see what happened to the pitch angle. So as you can see here, it's a sine wave. So this will change with the when you change the parameters. Let's make some changes, and it as 1000 and with four wings. Let's see a different one. And another thing is here you can actually delete these plots if you don't need a specific one. So now I have the plot 2, the previous one, the plot 3, which I just created. So as you can see here, actually, right, it doesn't have any, it does not have any changes to the pitch angles, azimuth angle curve, because it's actually depend on these link lengths. So let's give some kind of change, make it 9, and right, yeah, okay. Now you can see like what has happened. So like when you change the main link and code link and the second link, the sensitivity link, these lengths, these pitch angle variation will be changed. So that's basically about the second graph. And let's go to the third one. In the third one, we have the lift coefficient was the azimuth angle. So basically, here what we have is the lift coefficient was angle of attack was the lift coefficient. So since our actual input is the azimuth angle of the rotor, so here we have the variation of the lift coefficient with the azimuth angle. So for both lift coefficient and the drag coefficient. So the reason we are using this lift and drag coefficient is because when we are using the blade delivery momentum theory, which is the base theory for our software. Uh, so this code like develop the trust value using the lift and drag coefficient. So that's why these are really important. So you have these variations here, and the fourth one we have the trust. So this trust is for a single blade, a single wing. Uh, in the trust is actually displayed on two perpendicular directions in the x and y axis, basically uh, towards the uh, moving direction and into the perpendicular direction of the moving direction. So we have the vertical and horizontal component of this thrust here, and this, as I said earlier, this is for single wing. But since you have several set of wings here, you have to we need to analyze several wings simultaneously. So uh, the simultaneous analysis tool is the next one, and in here, so the fifth one is actually the resultant force, resultant thrust value of the horizontal and vertical thrust. So we have the resultant thrust here, and the sixth one, we have the cumulative resultant, which means that now here this is for single wing for complete cycle from 0 degree to 360 degrees. In here, this is for all the wings. Like when we combine all the wings here, so like there would be phase difference between these total thrust value. So these drops of the thrust would be minimized, like it would be reduced. So like once it reduce, the thrust value actually comes to some kind of this kind of a smooth sine wave. So according to these values actually. So these red color one is always the resultant total thrust. These colored lines are actually for the specific wings. So like wing 1, wing 2, wing 3, wing 4, it's like that. So this also varies uh, in both vertical and horizontal direction. So this is for the four wing situation, and in the six wing situation, you can see there should be a six wing one. I believe is this. Uh, okay, I have accepted four wings, all in all cases. So finally, we have the resultant thrust of all wings. So it's here, and you can see like what is the range of the thrust which it get. Uh, so,